topic is intrinsic hazard properties. I would like to introduce our speaker, Professor Elena Badetti from Ca Foscari University Venice.
Okay, thank you very much. So today we are going to briefly explain some of the main physical-chemical properties of chemicals and materials in order to support the advanced material safety assessment from both the ecotoxicological and toxicological point of view. So as you understood from the previous presentations, in the safe and sustainable by design framework, the concept as hazard assessment and risk assessment are integrating part of the framework. But it is fundamental to distinguish between what it is hazard and what it is risk. So you know that hazard is anything that has the potential to cause harm, while the risk is the likelihood that a hazard will cause harm. So in this case, the snake represents the hazard, but as you can see from the image, there is no risk if there is no exposure. This means that when we have to deal with safe and sustainable by design strategies, we have to know not only the chemical and material to which the target organism could be exposed, but also the exposure routes. This means that we have to know from which compartment these substances came, so this means soil, water, or air, which are the wave of exposure. So if we will have exposure because of inhalation, dermal contact, or ingestion, and especially the exposure concentration is very important. So if we have to understand which is the behavior of these substances, we have to know which are the main physical-chemical properties that determine not only how these chemical and material distribute into the environment, but also how they interact with the living organisms. So this means that they influence the absorption of these substances, their distribution in the body, their metabolization, but also their elimination. And they also determine how these chemicals exert their harmful effects. So in the case of chemical, these properties are quite well known because we know that, for example, solubility is strongly influencing the toxicity and the ecotoxicity of chemicals. In fact, if a substance is hydrophobic, or hydrophilic, we know that this influences the absorption, the distribution, and elimination. In fact, for example, if we have a molecule that is hydrophilic, we know that it's soluble in water, and so it can be absorbed by the body aqueous fluids, for example, such as the blood. While if the molecule is hydrophobic, it will be probably that it will be soluble in lipids, so they could be absorbed by fat-rich tissues, for example. And this is also determining the elimination from the body. So, for example, if molecules are lipophilic, they can be bioaccumulated by organisms, so depend also from the persistence of these compounds, and can also suffer biomagnification. And this parameter, the constant octanol water, is a very important parameter that indicates the affinity of these chemicals to lipids. Among the other properties, we have the molecular weight, for example. We know that small molecule can be better absorbed than biggest one, and of course, depending on their persistence, small molecules can be better eliminated than biggest one. Also, the degree of ionization is important, so the pKa. So you know that this is dependent also from the pH of the media, and of course, if the molecules is well ionized, it means that it is better soluble in water, while if it is neutral, we will find it more soluble in lipids. As far as the vapor pressure, you know that chemicals presenting high vapor pressure are very volatile also at very low temperature, so it means that that could be exposure by inhalation also at room temperature, for example. And finally, the chemical reactivity and stability have also an effect on the toxicity of these substances, because they determine the interaction with biological molecules and especially their persistence. So you know that chemicals that are toxic, persistent, and bioaccumulable are very dangerous. So what happens when we deal with nanomaterials? You know that nanomaterials present very innovative properties with respect with the corresponding bulk materials because of their nanometric size. So you know that they should present at least one of the external dimensions in the range between 1 and 100 nanometers. And in this case, it was most difficult to determine which are the main properties, physical-chemical properties, that determine the toxicity. But the scientific community was hardly working on this subject, and among the main properties that we know, there is the size. It is known that smaller particles are more toxic than biggest ones, usually. Of course, we are talking about particles of the same material, because, of course, they influence the absorption processes. But also we have to consider that smaller particles have a higher surface energy, so they are more thermodynamically unstable than biggest particles. Also the size have an impact, the shape, because they change the interaction with the cells. So it can interact, it can influence how these materials interact with the organisms. And in particular, the aspect ratio. So you know that this is the ratio between the longest and the shortest length of the particles, and this indicates if we are in the presence of fibers. So you know that fibers are more toxic than particles because they behave as asbestos. Surface area and surface charge are also important to be determined. As you know, when we deal with very more particles, the surface area highly increase, and this means that we are in the presence of many sites, active sites, for chemical reaction and interaction. So this, of course, will influence the toxicity of the material as well as the surface charge, because particles can be differently charged, they can be positively or negatively charged, they can be neutral, and this, of course, it can influence the absorption through the membranes. As far as the surface chemistry and functionalization, we know that the chemical composition of the surface is strongly affecting the reactivity, solubility, interaction with biological systems, because, of course, this is altering all these properties. And we know also that the systems are very dynamic, so they can suffer a lot of different transformation when they are dispersed in both biological or environmental media. Then, as far as the solubility and dispersion, we also know that if particles, nanoparticles, can be dissolved or they remain dispersed in biological medium, for example, but also in ecotoxicological media, these affect their bioavailability, distribution, and also their potential accumulation into the organs. And finally, of course, the chemical composition is fundamental, because there are nanomaterials that are intrinsically toxic, such as, for example, some metals. And then the crystalline structure is also influencing the final toxicity of these materials. So it is important to characterize all these aspects, because they all the transformation that can occur, especially on the surface of nanomaterials, can influence the final fate and behavior, not only from the toxical point of view, but also from the distribution of these nanomaterials in the environment. But what happens if we further increase the complexity of this structure? So in the case of advanced material, we have the combination of more than one component. So this can be chemicals, but also nanomaterials. But it's not said, I mean, we can also have advanced material that are not contain nano-based components. In any case, this means that we have a lot of different physical-chemical properties that derive both from chemical than from nanomaterials in case of structure like this. So the idea of producing advanced material is to obtain further innovative properties with respect to those observed with nanomaterials that are already new with respect to the corresponding bulk materials. We are talking about magnetic properties, electrical properties, and so on. So in this case, it is very important to understand which is the behavior of this advanced material, especially when we are performing the ecotoxicological and toxicological testing. Because, as you have understood, the surface can be easily modified and transformed. So if we consider a simple case studies that could be a core shell structure, then Andrea will better explain a nice example later. We can consider, for example, to have a very stable core coated by a layer that is a soluble metal. So two metals, one stable and the other one soluble. When we disperse, these materials in a medium, a lot of transformation can occur. So we have understood that the surface can suffer solubilization. Desolubilization can be favored by the presence of molecules and macromolecules in the medium. We can have the formation of an electrical double layer, and then we can observe the absorption of different molecules and biomolecules on the surface that are completely changing the characteristics of your material. So in this case, in which the core is stable and the coating not that stable, what can happen is that if in the medium we have some biomolecule, for example, that have certain affinity to the metal present in the surface, what we can observe is the formation of the corresponding metallic complexes. And the core could remain uncovered, for example. Then, if you're working in air, it can happen that you can get oxidation of the surface of your particles, and it could also happen that you have other molecules in your testing medium that have a certain affinity for the metal of the core. So we can obtain another structure. This means that if we have to evaluate the final toxicity of these advanced materials, we have to consider that at the end we could have a lot of different material in the dispersion testing medium. We can have the starting material because it's not said that all these reactions are complete, so we can have mixture of different components. So what happened? That different components can reach the same site at the same time, showing different toxicity mechanism of action, for example. So it will be very difficult to understand what effectively is giving toxicity of your material in the testing medium that you are using. So, of course, what we can observe are those called mixture effects that have to be evaluated and identified. So, this is not the last slide, but you have to consider that these advanced materials are always generally included in a matrix, so in the consumer products. So also the fact that these are embedded in different matrices further influencing the physical-chemical characteristic of your final material. So it is fundamental, of course, to understand the fate and behavior of advanced material, to well understand what you are working with, what you have to characterize, to analyze, and to define, determine which are the most suitable analytical techniques to be used to perform the correct characterization of your advanced material. So I'll have the floor to Eugenia that will better explain this aspect.
We have the chance to have also one member of the steering committee who happens to be our next speaker, Professor Eva Valsami-Jones from University of Birmingham. So I leave the floor to her to tell us a bit more about NSE community before giving her lecture on intrinsic hazard properties. Eva?
Thank you, Daniel. Thank you all for forsaking the beautiful sunshine outside to actually come and listen to me. One more thank you for Daniel for the amazing summer school. What an opportunity to be here. So, and also, of course, to Lang, the father of the school. It's been a long time since I attended in person one of these schools, and it's great to come back. My slide acknowledges my affiliation with the University of Birmingham and also the various projects that made it possible for me to join today. I will emphasize SiToLub. We have a big representation. You already heard your first SiToLub talk earlier from Davide. So one of the many projects that appreciated the summer school and joined. But also, as Daniel said, I'll say a few words about the NSE. Right, let me get this right. Network for Safe and Sustainable Chemicals and Materials, formerly known as the Nanosafety Cluster. We moved with the times and with the needs of the community, and we hope we are representing you all better by upgrading our agenda, our aims, and along with that, our name, of course. But the logo remains pretty much the same. And the special invitation I have, especially for the early career scientists today, is please join us and please take advantage of all the things that the NSE community has achieved over the years, so that they don't get lost, forgotten, ignored, and so that you guys can build on those achievements and bring science to the next level. Okay, talking about science. I love the title of the summer school this year, Innovating with Purpose and hands-on journey into, and I highlighted the words functional, safe, and sustainable. In the old days, functionality was the only objective. Safety could be considered a little bit later as an afterthought. Sustainability, maybe not at all. So now the trinity, functional, safe, and sustainable, is very important. And one of my scientific ambitions is to use material characterization and chemical characterization, why not? But we're focusing a little bit on materials in this summer school to actually do one-stop answer for all three questions, for safety, sustainability, but also functionality. So here's a long-term objective. We're talking about advanced materials, of course, today, and as I've been beautifully sandwiched between Elena and Andrea with a coffee break as the sauce, I will pick it up from Elena's introduction to advanced materials, just to say that we all used to be nano, but there's more to life than nano, so we are now advanced. Why advanced materials? My fellow nano NSC, Nano Safety Cluster at the time, coordinators, and I wrote this article 2021, From Small to Clever, implying that now we're not just looking at nanomaterials, but clever materials, materials that maybe have functionalities more than just size. So we started mapping, and in fact the NSC has been working on or has produced a roadmap for SSbD and AdMa. So this is the direction of travel, advanced materials. And my design of how I see advanced materials in relation to nanomaterials, and you might notice that this is a little bit nano influenced. I see nano as very often the functional element of an advanced material, but not exclusively, of course, as Elena already said. And I see many overlaps between different types of functionalities and nano functionality. In fact, the nanoscale is there, whether we pay attention to it or not. So I do. Okay, I promised to speak about analytical methods for advanced material characterization. I do primarily address the PhDs and postdocs in the auditorium, in the community. So the more experienced people, please forgive me for maybe saying things that you guys already know. Let me move this a little bit. Okay, that's better. So what do we want to know about a material? We want to understand the structure. We want to understand these 5 types of properties that they may have. And Elena earlier introduced phys-chem properties. I introduce it a little bit with an analytical point of view. So we want to understand the structural elements of the substance that we study and its morphology. These are perhaps the first things we look into, but also the chemical composition. So where in the periodic table does it map? And remember, we're now talking about complex, advanced, multi-layer materials, so it could map on many parts of the periodic table. We want to know the mechanical and physical properties. They may be primarily linked to functionality, but also occasionally maybe something that's more robust material might have implications for its safety and maybe also its sustainability. So it's not just about functionality. Thermal properties, of course, again, performance focused, but also it might suggest that this material decomposes easily, therefore implications to its safety and sustainability, and vice versa. Also, of course, electrical, magnetic, optical properties are the, again, characterization needs with a view to a particular application, but not only. Okay, so I'm sure you can't see all the techniques I've listed here, but this is just to give you a first flavor of all the analytical possibilities one has when we decide to characterize a material. So in terms of structure and morphology, the classic techniques everybody, or almost everybody uses. And I appreciate some of you might be life cycle analysis experts. Maybe you never come face to face with the TEM or an XRD, but you will come face to face with what comes out of these instruments. So maybe there is a purpose to becoming more familiar with the analytical techniques. So there's a whole range of techniques that will give us information on structure, physical characteristics of materials, and of course there's a whole range of techniques that will give us information on the chemical composition. I'm not going to go into details of each one of them. They're there, you've got the slides, you can look at them, but it's just, again, just to give you a flavor of how the methods we use to characterize something change as we change the kind of information we require from this particular material. A bunch of techniques for thermal properties, TGA, thermogravimetric analysis, DSC, thermal conductivity. Same for mechanical properties. These tend to be a little bit more specialized properties, and therefore perhaps fewer techniques to choose from. And electrical, magnetic, optical, again, a bunch of properties. Some very specific for one property. For example, SQUID is just for magnetism. You won't use it for anything else, but UV is a workhorse as an analytical method. And again, I hope the words that come out of my mouth give you a sense of, characterization is a very broad field, so finding your way around it, maybe you need a little bit of help. Hopefully this is providing with some of the help you need. Okay, so what kind of help do you need? You need to make some decisions about how you go about characterization. So I guess the first decision is, what do you want to know? Do you know anything about your material? Did somebody come with a bag and said, please tell me what's in there? So starting from somewhere, maybe basic composition, basic structure, and working your way as you discover more about your material. Then you need to match the method, and you will see in my next slide a little table of how to match method to property. So you never use microscopy if you want chemical analysis, or unless if you have an instrument that does both. I'll speak about mixing methods a little bit later. But again, match the method to your characterization needs. Then decide what system you've got. So again, to bring the joke about someone coming with a bag of stuff, asking you to characterize them. Is it solid? Is it liquid? Is it a suspension? Is it nano? Is it organic? Is it inorganic? That's the kind of questions that you need to address in your characterization. Then the topic is quality versus practicality, and that is my very last slide. It's a spoiler now, in case I'm too slow to get to it. My very last slide is about the Rolls-Royce of characterization, but there's a lot of smaller, less expensive methods that you can use, and of course, what you have access to and what you can afford to do might influence your choice of characterization method. Speed is important, and also back to the original question of what you want to know. And finally, use complementary methods. So, for example, I have a couple of case examples here. So if you want to know particle size, you're in the nanoscale, so maybe you choose TEM, or if you're in a larger particle size scale, an SEM. And TLS, because TLS gives you hydrodynamic diameter in a suspension. The other two methods, TEM and SEM, would give you solid state dimensions. XPS and FTIR is another good example of complementarity. X-ray photoelectron spectroscopy gives you surface properties. FTIR gives you functional groups, and usually we functionalize surfaces, so they are nicely complementary. Okay, and stay up to date with methodology developments. You will be surprised, for example, for those of us who use ICP-MS inductively coupled plasma mass specs, you see that newer generations of instruments do all sorts of things that you never imagined possible with the older generation instruments. So that might be something you want to keep an eye on as your needs become more advanced, or as you move from one project to another. Okay, this is just, I literally flashed this table to you just to give you an idea of, there's a characterization need you have, and there's a choice of instruments. Some of these will be your first port of call, so the first method you'll choose will be from your primary methods list, and then you might want to need a little bit more. So for example, again, just looking at the first line, if you want a chemical composition, you might choose ICP-OES, ICP-MS, I mentioned both methods just earlier, to start with, and then maybe you realize there's carbon or nitrogen or sulfur in my sample, so you might need to also go for CH&S analyzer, but that might be your second choice, not your primary choice. And you have to be agile in your choice of analytical solutions to the problem. I won't go to the rest, but it's there for anyone to take a look if you want to. Oh yeah, and I mentioned method hyphenation. Again, latest technologies sometimes offer us an instrument that can do multiple things, and by that I don't mean, multiple element characterization, but actually multiple approaches. They're called hyphenated instruments, and one example from my lab is we have a TGA, thermogravimetric analysis, so thermal decomposition properties, IR, infrared, so structural chemical properties, JCMS, so organic composition. So you have 3-in-1 instruments characterizing your sample, all on the same spot. So imagine how much more information you get from a hyphenated method that you would otherwise from doing the samples individually, and also the time saving, of course. And please don't ask me how often this instrument breaks. It breaks a lot. Okay, I'm conscious of time, so I'll try and speak a bit faster. A few years back, we finished coordinating this project, ACE Nano, which was actually developing a method toolbox for characterization. The website is still live, hosted by one of our partners, Douglas Connect, but it's not been updated. But it might, for some of you who want to just get a general idea of characterization methods, it might be a port of call. So you would get a list of techniques and endpoints. Some of these techniques, we actually do have a lot of details because there were techniques we worked on during the ACE Nano project. So for example, BET surface area analysis has a full assessment with case examples. Some other methods don't, but it's there for anyone who might want to know a little bit more about some of the characterization methods used. And it is a little bit out of date, 2 or 3 years out of date, bear that in mind, because analysis moves fast. But it's a starting point. Okay, I have a case study on MACSINs. I'll say very little because, time is of essence. I'll just briefly mention MACSINs are one of those all Dunsin advanced materials. They're basically 2D materials, metal carbides. The slide actually shows you have a precursor called MAX that's made of MAX, in which you degrade into a MACSIN, you remove parts of the components, you remove the A element basically, and end up with a far higher surface area and far more reactive 2D material. That's the simple way of describing the synthesis of MACSINs. They have lots of applications, primarily in the energy sector. The project I will literally spend 2 minutes talking about was one where we were looking into transferring the application from the energy sector to the environment. Can we take advantage of the large surface area of MACSINs to use them as environmental remediation tools? And in the process, we had various challenges. So the energy sector can possibly, although I'm sure the SSbD people in this room will disagree with this statement, but I'll say it anyway. So in the energy sector can possibly afford more expensive materials. The environment sector definitely can't. So we were looking to solve some of the problems about the costs of producing MACSINs, also some of the safety issues, and also some of the surface area issues to improve their functionality. We worked on producing using cheaper precursors, so where you used a metal, titanium, we used titanium oxide, a cheaper material, but also a safer material because metals tend to be a little bit reactive, whereas an oxide is less reactive, so easier to handle in the synthesis process. We looked at alternative carbon sources, so we looked at replacing graphite with activated carbon to play with the surface area. And we also looked at temperature synthesis. Lowering the temperature synthesis makes the material far more sustainable because it costs less to synthesize it. So we played with a range of temperatures and optimized to the chosen one. I will literally, this is just the slide on the MAX synthesis. I will run through those slides, but I will just focus here on the key adaptations. So I mentioned substitute titanium for TiO2, reduce synthesis temperature, use activated carbon, and this gives us safety, sustainability, functionality improvements on the original formula we had for our synthesis. I will literally just run through these slides to show you these are the kind of graphs you might get when you're trying to characterize your material. So you have TGA on the left, XRD on the, on your left, just checking, XRD on your right, as means of understanding thermal decomposition, structural information. These are the top 2 slides, show you these 2, whoops, I completely pressed the wrong button. Right, okay, so these 2, if I Okay, these two are the MACSs, the pre-surface area enhanced treatment, and these are the MACSins, where you can see a lot more surface area, a lot more roughness and structure to them. BT results, and we were able to demonstrate that we increased the surface area of the material. Uptake of a number of BTEX substances, just to show that it actually functionality improved. And in fact, our increased surface area material had a better function to absorb those chemicals. And it was very nicely performing in repeated tests. So uptake, then removal of the metals and reuse. So a nice potentially case study to talk about, and I already told you the main features or the main purposes of this study, so I'm just literally moving to my last slide, which says when sky is the limit. This is synchrotron results from Diamond, the UK synchrotron. When I was talking to Andrea earlier, he said, oh, maybe some of the students might want to visit Diamond. If you do, please talk to me, and I'll be happy to collaborate if you want, or guide you to how to apply for access to Diamond. What you're looking at here is a DAFNID. On this side, you actually see a map of calcium on the DAFNID, and that gives you the semi-skeleton. It doesn't really have it has a chitinous skeleton, but it gives you the structure of the DAFNID. And you can see head, tail. And this is a map of the distribution of europium-doped nanoplastics in the body of the DAFNID, which allows us to understand uptake and removal of nanoplastics from organisms. And actually the interesting feature, just for your eyes only, don't tell anyone, this we think might be the brain, and we can see accumulation there of the nanoplastics. That's all I want to say. Thank you, and please come and talk to us. I'm here till Friday. Thank you.
Thank you very much. So now we have the opportunity for questions. If you would like to ask questions to Elena or Eva, now is the chance. Alberto is first.
We need microphone. We have also online listeners. Thank you very much. So, well, very nice talks actually. The three talks actually. So I have a question to you, Eva. Well, probably it could be like at least like 3 questions, because the case studies were very interesting. The thing that you showed like with the nanoplastics at the end was very interesting in Daphne as well. But my question was more related with the characterization methods. I think, like, for example, in some projects, what we try to do is to try to organize the methods, the characterization methods, in an order, like from the less complex methods to the more complex methods, cheaper methods, more expensive methods. And I saw that you organize like in primary methods and then secondary methods. Is this based on the level of complexity, robustness, cost? And also, like, just to wrap up this question, like, so do you have any recommendations in terms of what is like the, initial pack of, characterization methods that we should perform, and then a more complex and more robust pack of methods?
Thank you, and that is an excellent question, Alberto. So I structure them in order of this information you need first, and the rest of so the first column is what I would do first as a method. And you see, it wasn't just one method. In most boxes, there were several methods, because there's no simple answer to your question, and I would love to help you do what you're planning to do if you need help. But it's because materials vary so much, and don't even start on chemicals, so it's difficult to choose. But my table was basically start here. If you need more information, go to the second column. It was as simple as that.
Thank you. A follow-up question to that is that I noticed that all your microscopy were classified into a secondary a secondary selection, the MS analysis. So can't I start my analysis from MS, GCMS, LCMS, because your MS are all in the secondary section?
So your mass spec methods will be more on the chemical information. We tend to, for better or worse, and maybe something to rethink about, we tend to start by physical characterization, so size, physical structure, and let's face it, we all love microscopy. it's more visual, so you might start with microscopy, but you're right, and if you already know what your material is and you just want to know, oh, do I have any titanium and any rare earths in my material? Yeah, go for MS, of course.
Lang? No? No. Now is the time for our last presentation of this session, and this is Andrea Brunelli. He will tell us a bit more about the advanced properties that support ecotoxicological and toxicological testing.
Thank you, Daniel. So welcome to the school, to everyone. So I will give you a very brief introduction, if the slides start or not. Anyway, I can, okay. So I'm Andrea Brunelli, I'm working at the University of Venice, I'm a researcher, and I will give you a presentation about a case study that's linked quite a lot on the presentation that have been previously heard about from Elena and Eva. So in this case, we have a case study dealing with in construction. So one of the big issue right now in our period, it's about air pollution. So this case study deals with try to cut off the nitrogen oxides in the air, try to convert them to nitrates that could be considered a little bit more environmentally friendly than nitrogen oxide in the air. And usually there are already a lot of products that can try to tackle this challenge, made more or less quite a lot about titanium dioxide-based nanoparticles that can lead to actually photocatalytically react with nitrogen oxides and obtain nitrates. But the thing is that according to the International Agency Research on Cancer, titanium dioxide nanoparticles are now classified as potential carcinogenic because of the potential inhalation of these particles to humans. This is why this case study is about try to replace the titanium dioxide nanoparticles with this advanced material that is composed by two different components, as you already heard about. The advanced material can be nanomaterials or also chemicals inside. In this case, we have a core of silica dioxide, and the supplier told us that was a kind of layer around this silica dioxide that is made by zinc oxide, okay? So the idea is to use zinc oxide as a replacing material of titanium dioxide, and then silica dioxide was used to improve the performances of zinc oxide in the final product that is a mortar that can be applied to the buildings. So starting from the material characterization, material synthesis, what we have here is that the material started from the nanoparticles, silica nanoparticles that are commercially provided, and then they were mixed with a chemical, okay? So it's not nanomaterial in this case, so it's a salt, it's a zinc acetate salt. Through some of the different steps in the lab, we obtain this silica dioxide and zinc oxide advanced material. Of course, then this was added to the final product to try to obtain and achieve the aim of convert nitrogen oxides in the air to nitrates. According to this case study, we selected 2 different type of reference materials or benchmark. It depends on the definition that you would like to have it. But anyway, during the synthesis, we characterize the material and we use zinc oxide nanoparticles as a reference material because the outer shell of our advanced material is made up of zinc oxide nanoparticles. And then during the use phase of the material, so in the final application phase, I would say, we compare some of the characteristics of this material with 2 different mortars made by or titanium dioxide nanoparticles based or silica fume based that are already available on the market. So starting from the characterization point of view, as already Eva told you, so we started just from the TM analysis, try to look at the differences that we can observe between silica dioxide nanoparticles and the advanced material, and we use zinc oxide nanoparticles as reference, as I told you before. And what we observe is that more or less the average diameter by TM was a little bit similar between the silica dioxide nanoparticles alone and the silica dioxide particle with the zinc oxide layer on top. So in this case, we look at the size and also at the shape by TM. And as far as the zinc oxide nanoparticle is concerned, we observe a kind of higher particle diameter between 100 and 200 nanometers. That was our reference material. Of course, we look at the shape also with SEM microscopy. So here you have an idea about 2 different types of samples. One directly from powder. We look at the sample by the powder sample, and then also we deposit the sample. We prepare dispersion that we deposit a drop on the for being analyzed by CM. What we observe is that more or less we have the same characteristics and the same shape, I would say, between, again, silica dioxide nanoparticles alone and the advanced material that is made also by zinc oxide. So we move on. We also had, characterized the material by looking at the chemical composition in this case. So we would like to understand how can we understand if this is actually coated or not by zinc oxide. So we use ADX, in which we can observe different mappings of the different elements. So this is a, I would say, qualitative technique. It's not quantitative, but can give us an idea about the elemental composition of the material. So we compare the map of the zinc on the sample, and then the zinc here, the silicon here, and then we merge the 2 maps. We observe that it was a kind of agree of these two maps on top between them. So we can understand and we can say that this material is actually composed by silica and then kind of, I would say, a layer, not nanoparticles of zinc oxide. Then we look also at the surface chemistry. So we used FTIR spectroscopy and also BET spectroscopy. What we observe in this case by FTIR, we observe the stretching and bending of characteristics of the bonds between silica and oxygen, silicon and oxygen, and also zinc and oxygen again. And from the BET, what we observe is that if we compare the specific surface area of the silica dioxide alone and the advanced material, we observe a decrease in the specific surface area. This could be occur because we have this kind of layer on the surface that can, I would say, decrease the surface area because some of the pores of the silica alone were occupied by zinc oxide. Okay. Then we move on again to look at the chemical composition from a qualitative point of view. In this case, we characterize the samples by ICP-OS. This is not a Rolls-Royce, as Eva told me before. It's kind of well-known technique, but it was it can be anyway used depending on the type of material that you have. And in this case, we managed to understand the composition of the two different components in our advanced material. The results showed us that we have around 80% of silica dioxide and then 20% of zinc oxide on top. No, I mean on top you cannot say from the ICP-OS, but we can say just the percentage of the two elements. We also characterize and we look at the dispersion stability and the surface charge of these materials by quite easy to use techniques, I would say. So we exploit light scattering techniques like dynamic light scattering and electrophoretic light scattering to have information about the hydrodynamic particle size, so the size in the liquid that is different from the size from the TM. And we look also at the surface charge of our particles, and then we also investigate the dispersion stability of our sample. So after the dispersing the powder in a medium. So what we did basically, we compare the dispersion stability of the advanced material compared with the precursor, I would say, so the zinc oxide and the silica dioxide, by increasing the complexity of our media, so moving from the ionized water and then to fresh water, that is this one. Then M7 is quite more close to fresh water and is used for testing Daphnia mania. And then we move at least to artificial marine water. What we observe from this characterization is that based on increasing the ionic strength of our media, we observe a kind of destabilization. So we observed a higher hydrodynamic diameter, a higher sedimentation velocity of the particles, and the zeta potential that went close to zero if we move to the artificial marine water. Then we look also at the solubility of our material, since we have this core shell structure that is silica dioxide coated with the zinc oxide. So in this case, we again use zinc oxide as reference material. So we prepare our dispersion. Then after different time points, according to the toxicity testings, we look at the supernatant after some time. And what we observe here, so you have different media in these 4 graphs. We look at the zinc dissolution over time. What we observe is that the dissolution of zinc, of course, this was normalized on the same concentration of zinc. The dissolution of zinc was higher if we consider the advanced material with respect to the zinc nanoparticles. This probably was related to the different structure, actually, of the material, because on one hand, we had this very thin layer of zinc oxide around the core of silica dioxide. In the other hand, we had just quite larger nanoparticles, the zinc oxide nanoparticles, that were, as you remember, between 100 and 200 nanometers. Last but not least, we also look at the solubility from the final product, actually the mortar. So in this case, we compared the solubility of our advanced material that was embedded in the mortar. And as reference materials, we used 2 different materials. So one based on titanium dioxide nanoparticles and the other on silica fume nanoparticles. Again, we look at the solubility over time according to the time points that are used in toxicity testing. And what we observe here that there was no release of zinc or titanium in all the samples, so this was good. And we observe only the release of silica, as you can see here. So all these mortars were made anyway of silica, even also the mortars based on titanium dioxide nanoparticles. So we observe a statistically significant difference only of the dissolution of silica only for the higher on the sample with higher amount of our advanced material that is in 5% weight. Yeah, so I end my presentation. If you have any question, I'm here. Thank you very much.
And now we are going to be having on stage the father, as we heard today, of this kind of training school, right? Tran, from the Institute of Occupational Medicine in Scotland, right? This is in, where in Scotland actually?
Sorry?
Where in Scotland? Edinburgh?
In Edinburgh.
Edinburgh. So, okay, Tran is going to talk about nanoenergetics and how this kind of connects to toxicity and prevention measures.
Yes.
Stage is yours. Looking forward.
Hello, good afternoon. So here I am. I'm going to talk to you about this entity called nanoenergetics. And before I move further, I want to make a disclaimer that I would like to say that this presentation is in no way how to teach you to make bombs, okay? So you hear that. But I'm going to start and you will see how reality will always surprise us. What you see in here is the accumulation of all the work that has been done and summarized this morning. But now they are ready to be used for something that none of you expected. And it's now happening. And I hope that this presentation will help to galvanize all of you into readiness, okay? So, nanoenergetics, what are they? It's just a new name of an old thing. They're not new things. So you'll be so surprised that you meet old friends here, but they are being used for new application and how efficient they are, okay? So, energetic material in general has been used years ago. You know, there are a mixture of pure component and chemical substance that could release that enormous amount of energy or gas when you ignite it. You understand? This is where I'm coming from. This kind of materials has been used ever since humanity had the burning desire to burn each other. We already had this idea. But to fast forward our historical clock, in the past 2 decades, the research on energetic material has realized that they can tap into nanoscience and nanotechnology. This is where we come in, okay? And how they can capitalize it. So they're really interested in our nano-sized material. Why? It's because this morning, you guys have been talking about nanomaterial all the time. And what is so special about nanomaterial is amazing surface in relation to mass. So for per unit mass, you get huge surface area. And with huge surface area, you can attach all kinds of things into the surface. You understand? And since they are so low on mass, they are ideal for transport. Okay? And this is what people want. They want very light material with huge surface that are very easily transportable, that can be adapted for the new technology, the new missile, the new drone. You can think of it. All of these new machines has a problem with heavy load, and this is going to solve it, okay? And of course, as the material become closer and closer to each other, the bond between the chemical component become closer and closer to each other, and therefore, any reaction can be controlled. You can control the reaction to the ignition time that you want. So it can improve the reaction rate by being so close to each other, and it reduces the ignition delay, because if the material are far apart, it takes longer to react, but if they're so close together, it can ignite very easily. And if that's controllable within the level of safety that you're in, you can make these materials, okay? So just a bit of history, okay? Initially, at about 25 years ago, the kind of material that they used to make nanoenergetics materials are just metal particles, the metal nanoparticles that you guys have in the lab, mainly aluminum, okay? And they first tested as rocket propulsion. But why do you need propulsion to boost a rocket? You can use all this energy release for other, even nastier things than that. And in the second half of the 20th century, now we're coming to your generation, okay? Especially the last 20 years, they discovered that if you mix the oxidizer, metal oxide, with fuel, okay, at the nanoscale, it improves the diffusion distance between the chemical species, and of course, being so light, it enhances the surface over volume ratio. Okay, so this is now the combination of choice. So, at this moment when I'm talking to all of you, the work is still in progress. We are now talking about nano composite now, okay? Because if the surface area deliver, then the next step is what you attach on the surface area to make it even more reactive. And this is where the sky is the limit, okay? So if you use nano-sized oxidizer with fuel and extra additive, it can be a source of extremely high heat release, okay? And you can tailor it. The burning rate can be as you like it to be, and the combustion efficiency is amazing. That is what they discover, okay? And because of all of that, of course, there is a huge demand of this material for explosive, okay? It's light, its combustion capacity is super efficient, and it releases an enormous amount of burning heat, okay? So, if you think of the core of the nanoenergetic material, then on the gray circle around it, you have the next generation of explosive. You can actually use it for energy storage, but also nanothermite, and you can use it also for fuel, propellant, you know, rocket fuel, that kind of thing. And the application on the outer circle there is to use it on drone technology, because one of the biggest drawbacks of drones is that they can carry only a limited load. So if you lighten the load and you give twice the bang, this is what they want. This is the shape of thing to come, okay? So they are really drawn into making very light and powerful explosives that can be carried by very mundane drone that can fly longer distance now because they carry lighter load. And this is what they are really interested in. And this is not the future. This is now happening, okay? So, having said about nanoenergetic, I want to say to you about how they can be used to improve explosive, okay? Now, by no means, as I say, this should be an encouragement for all of you to go home and think over this thing at home. Please don't, all right? But since we are between scientists in here, the information that I give you is enough for everyone in this room to look further into it. We have already gone through the first phase in which they use the traditional material. And the limit has been reached as to how much you can exploit it, okay? So they discover in the new war is that by reducing the size of things, you can carry it further, you can carry more, and you can deliver an extraordinary bang for the buck, so to say, okay? And, you know, the explosive of yesteryear, like TNT and so on, is going to be phased out in the next 5 to 10 years. You're not going to use the C2 explosive anymore. This is now into a new phase, okay, with a new explosive power, okay, and of course they make use of the nano size, because the larger the particle, the slower the speed of reaction, and especially the density of the formulation is very limited, okay? So if now you can add all these nanoparticles together, you can make a massive bang. For example, like the picture. You see the picture to the right there. That is a typical big bang you can make for a reasonable low mass, okay? And if you can manipulate the surface, then the sky is the limit, because there's such a huge surface. You can do whatever you like in addition to the large surface on it, okay? So now I move down to the specific. There has been already a series of these bombs been made, and some of their name will remind you how close they are to what we are doing in our science, okay? The first one is called a thermobaric bomb, which comes from a Greek word, which I asked Eva in here to testify. Thermo means heat and baric means pressure. That is the first generation of these bombs, okay? But now, the later version, they're known as the aerosol bomb. Now that's become familiar to what we are doing, because what they generate is an aerosol of nanoparticle, okay? And the last thing is called a vacuum bomb. You know why it's called a vacuum bomb? Because when you expose metal oxide, it reacts with the oxygen in the atmosphere, and it causes an ignition. And the ignition consumes the oxygen in the surrounding. It sucks up all the oxygen, and basically it pulls everything inward, like an implosion like this, as it explodes. That's why it's called a vacuum bomb. It creates a vacuum. So apart from killing people, it also asphyxiates people, because it sucks up all the oxygen. Now, the way they do it is that they have two explosions. The first explosion is to ignite the aerosol, and the second explosion is to start a reaction. And once you have that second explosion, the first one is to ignite and start the ball, and it's aimed at exploding it at a certain height, okay? So it can control. And once it boom first, then the second boom is to ignite it, okay? When the second charge detonates, this cloud, it creates an absolutely massive wave, shock wave, okay? And because of that, they are so useful for the military, because you can use this to destroy infrastructure. You can destroy bunker, you can destroy tunnel, you can destroy underground, you can destroy anything you can think, because of this blast that it created. So I bring you back to what we say this morning about toxicity, okay? You remember what has been said by all our predecessors, our speakers this morning about nanotoxicology. It's about the potential hazard of nanomaterial. And the nanomaterial that I show you today is actually not radically different from what you guys study, okay? So we try to understand what is the physical-chemical characteristic that can cause the toxicity. One thing is missing this morning, although it's been touched upon, is the pharmacokinetics and the pharmacodynamic, okay? That unlike the big particles, the nanoparticle, once it gets into the body and it has access to the blood system, it circulates to secondary organ, okay? This is a very important finding of nanotoxicology, is that if you inhale big particles, they mainly stay in the lung, yeah? But if you inhale nanoparticles, you soon find them distributed in the liver, the kidney, etc., okay? And we found that out in the context of nanotoxicology using very tiny dose, okay? Because what we are interested in is accidental exposure. We're not talking about massive exposure, okay? So we found this out. However, now you are facing with a reality in which the dose that you are exposed to can be massive, okay? And I forget one more thing is that Eva this morning showed that to visualize and see this thing, you need very strong microscope and all this kind of thing. Well, currently, Eva, in the field hospital at the front, the only machine we have is the X-ray machine. And they are useless at actually seeing it. I have spoken to Ukrainian surgeons at the field, and they describe, because they don't know what we're doing. And they say that they have never seen the type of injury like this before. And the word, and this is the exact word that they use, they say, we see the liver and the secondary organ away from the injury. They use the word, the dusting of the organ. It's dusting, that means it's very fine material that you cannot quantify it. All you can say is that there's like a haze inside the organ. But the X-ray machine cannot possibly quantify this kind of thing. So that's the first limitation of where we are, okay? So quickly, as you can see, when it goes bump, the first thing is that it blasts your lung. You will be ruptured with your ears. There will also be eye rupture, okay? Then you have the penetrating trauma, the shrapnel trauma, okay? And the third thing is it can break your bones and so on. Then you have the burn to the skin and so on. And finally, you have the fifth one, which is the chemical reaction, okay? You get chemical burn, radiation, and so on. Okay, so if I summarize that, traditionally, we only have the 4th stage of the injury. But now with this new type of thing, you have to include illness into it. The chronic effect from the retention of these particles that cannot be clear from the body. The genotoxic effect and everything that you mentioned has now become real, okay? And the last is the psychological trauma for the victim who suffered from it. Okay? So, as I say, the word, and not a word that the surgeon from the field come back. It's the first time in all this year I work as a toxicologist, I have never heard of the word hyperinflammation. This means that when it goes in there, it causes an absolute acute inflammatory response, okay? And it leads to all kinds, if you cannot remove it, it stays in there, then you have fibrosis, cancer, etc. Okay, so quickly, how do we deal with this? Well, I jumped one slide before I say about this, is that currently, guys, there's no regulation. Unlike everything we worked this morning towards regulation, here there is no regulation. There's no regulation to speak of, okay? So everybody is for themselves when it comes to this. And so we have to develop protective equipment because the way to protect ourselves with regulation is not available. So the only thing we can think of is developing protective clothing. And currently, amazingly enough, they have been using carbon nanotube as body armor. The carbon nanotube is very resilient, and it can stop a bullet shot at it. And it can dissipate the impact of the bullet and therefore reduce the punch of the bullet into the material. However, if you look at the picture below, the carbon nanotube tend to stick together as these cotton weaves, and there's plenty of holes in the between, which is fine for the large projectile. But as your projectile gets smaller and smaller, it begins to go through this thing easily because of the gap, basically. So we had to think of new way of weaving this material, you understand? So that you can close the gap or you can use many layers because these materials are very thin. They're very amenable to a new technology, new textile that we can use as protective clothing. And the way to do it is the experience we have with the anti-COVID filter. So if we can use carbon nanotube and we use the anti-COVID filter to actually make very close filter together, we will have something that can stop this material. And this is something that we have to aim for because as trust me, there's no regulation whatsoever. So I mentioned it here. I did through all the ethics regulation and so on, and basically you just pay lip service to it. And here there's something very interesting. In our work, you remember, they use nanomaterial in sunscreen or whatever. And then when you say you have to declare it as nanomaterial, they say, no, we give you the chemical description, that's enough. That was what we do in nano regulation. But now, when it comes to this thing, there are regulations on chemical weapons, yeah? But here you say, well, is that a chemical or is that a material? They quickly say to you, no, this is a material, not a chemical, and therefore, no regulation needed. So there is absolutely no regulation. So, as I say, we need to develop all these things in order to protect ourselves. And if I think I sniffed. I just want to show this picture before I stop. If you look at this the top picture is what happens when you have a blast lung. That means that your body in the front is only bruised, but there's no cutting injury. But the blast can be so strong that your lung is totally damaged. It's red blood, okay? And the middle picture, I'm sorry it's not very clear, but if you look at it, this poor kid is lacerated. You can see that. Now, if you imagine as the particle becomes smaller and smaller, the density becomes denser and denser, the distance between two wounds will come closer and closer to the point that you see down there. What you see is a burn wound, okay? And this is what we are going to be dealt with right now. In a sense, when I talk to the people who work in this field, I was amazed how well-versed they are with our literature. They read everything that we write, especially about the potential toxicity of this material. But whether they care about toxicity like we do, that's another question, okay? And one of them put to me a very simple economic statement. They say, if you kill somebody, you kill somebody. That's the end of it. But if you maim somebody, if you injured somebody with this kind of thing, the after effect of looking after the person with all this chronic disease is an additional economic burden to the country after the war. And if there's a lot of invalid, ill people due to this, then it's actually better than kill people. That's what they say. And one final thing before I finish, I show you something that relevant to Alberta. You see, this is an experiment with their bone. You can see on the floor there the residue. So environmental exposure on a large scale is happening right now. There's huge environmental exposure on the floor, or it could be on water, it could be anything you like. I spoke to my Ukrainian colleague, and they say that it would take years to clean up the Ukrainian countryside after the war because of this. So that's on that point, I will stop, and I hope that is relevant, and I hope that will bring you back to reality, that this is something is happening. It happened not as we anticipated it. When me and Eva, when we worked, it was on the basis of a few milligrams. Now you're talking about massive. And probably the industry that make the most of these materials is the defense industry. But how much they make, they're not obliged to declare how much they make. But the history of this shows you clearly where we're heading, and it's happening, okay?
Thanks a lot. Thanks a lot, Lang.